Yes? It's loading. Okay. Simple harmonic motion. So we'll do this in two parts. We'll continue it next time. Yeah? Okay. So, simple harmonic motion. Let's recap. We've seen motion in a straight line, motion in two dimensions, motion in a circle, and now simple harmonic motion is motion like with springs. So it's motion that kind of goes up and down like this. This is simple harmonic motion. It's a special type of motion as well. So, what exactly is the definition for this type of motion here? An object is undergoing simple harmonic motion, then the force is proportional to the displacement and acts in the opposite direction to the displacement. So I'll explain what that means now in a moment, but if you can just write the definition down. Okay, you got the definition? So what I mean by this is, like with the spring, the bigger it is, the more force is going down. And it's going down if the spring is moving up. So for example, the spring is going like this, okay? As the spring is going up, which way is the force pointing? Down. If the spring is going up, the force is going down. And the bigger the displacement, the more force is pulling it down. So when the spring is up really high, the force down is really big. And it's going down. Of course, the force is not going up, because if the force is going up, then the spring would keep getting bigger. Okay? So this is a simple harmonic motion. So I actually already did the imagination part. But the graph here is the velocity. And this is not surprising. So like for example, if I have a spring and I pull it here, and then I let go, what happens? Does it move up or does it move down? It moves down. So you can see its speed is, its velocity is negative at the beginning. And then what happens? It moves down and then it slows down and then it stops and then it goes up and then it goes back down and it keeps going up and down. So you can see that it keeps going positive and negative, positive and negative.
Yeah. It doesn't go to its full length.
Hey.
Sorry.
Huh?
It doesn't reach its full length, right? That when you pull it.
I know, we won't worry about things like that, that's a separate thing. Right now I just want you to see that this is what the graph looks like. I don't need you to draw it, because I think we can all imagine this. As it's going up and down, its velocity goes from negative to positive. Yeah? So this is what the velocity time graph looks like for simple harmonic motion. Oh great, who are you talking to? Tell me who?
Somebody else from China.
Someone in China? What time is it in China now? Earlier?
Maybe 6 p.m.
Oh. So this is your friend from China saying, just home from school, hope you're enjoying your day. Lol. Okay. Right, so in simple harmonic motion, we have three terms that we also use in circular motion. So think about the motion in a circle, and then the motion, simple harmonic motion. What terms do you think would be the same? Well, time would be one, okay? So in circular motion, you have the time for one. So what do you think the time is here? For one, yeah, to go from down to back up. So you have one time. In circular motion, you have frequency. How many in 1 second? And the same here, you have frequency. How many in 1 second? So the three terms are frequency, time. Anybody want to guess what they think the third one might be?
Omega.
Yes, omega is the third one. And these mean the same thing, except for the omega. Because in the circular motion, the omega was for the angle as it moves. But here, where's the angle? There's no angle, it's just moving up and down. So it has a different meaning for this motion. Okay. Still a type of speed, but it doesn't mean the same thing. There are no angles. So the way I'm trying to explain what the omega means is with this picture. If you look at the wheels, what type of motion is this? Circular motion. And if you look here at this part that's going forwards and backwards, I mean, you all have seen trains before. So this part here is going forward and backwards, and it's making the wheels turn around. So this motion here is simple harmonic motion, and this motion here is circular. So the T, if it takes 1 second for the wheel to turn, then it will also take 1 second here for the piston to go backwards and forwards. This is called a piston. So if it takes 2 seconds for the wheel to turn, then how long will it take the piston to go out and back? Also 2 seconds. If the frequency is 5, the wheel will turn how many times in 1 second? 5 times. So the piston will also go out and in 5 times in 1 second. So that's the T and that's the F. What about the omega? So if the omega is 1 radiant per second, it means in 1 second the wheel turns 1 radiant. And then the piston will move a little bit. So this is how we can imagine the omega for the simple harmonic motion. If we stuck a wheel at the end of the simple harmonic motion, the omega would be the angle there. Okay? So I know the omega is difficult to understand here. But if you want to try and understand it here, you can imagine it attached to a wheel. Okay? It's difficult, I understand it's difficult. But I think the T and the F, we understand clearly.
What would be the unit of omega in this?
It's still the same, radians per second in the simple harmonic motion, yeah. Which seems, like I said, it seems odd because there's no angles. But we can kind of imagine an angle this way. Yeah? So So look, I said we'll do this lesson in 2 parts. So the only homework you have for part 1, the only homework you have is I want you to look at this animation to try and help you understand this. So if you can just take a picture of this, or you can watch the video later to get the link. Have a look at this animation to try and help you see the relationship between the simple harmonic motion and the circular motion. Got that?
Yeah.
And yeah.